What does this slide from 1911 and how I destroyed my 16th birthday present have in common? Today, we're going to look at exposure time. Looking through the collection of photographic slides we found in the astronomy slides cupboard, the vast majority include extra information about what the object is, where the image was taken, and in some cases, what the exposure time was. So, for this one right here, it had an exposure time of 1 hour and 40 minutes. It's also a negative of the image for no clear reason, and was taken on Christmas Day 1911. When taking a photo, either on film or with a digital camera, you can adjust the settings on most cameras for how long the shutter stays open for. The simple version of this is that the longer you leave the shutter open for, the more light you let in. This allows you to detect fainter objects by giving them more time to have enough of their emitted light reach whatever type of detector is at the back of your camera. The A-level and beyond reason for this is similar, but works on the fact that you know that light can be treated as particles called photons. For photographic film, this reacts when the photons come into contact with it, so the longer you leave the shutter open for, the more photons can hit each part of the photographic film, leading to a greater chemical reaction and more discoloration on the film from its original tone. For digital cameras, they have CCDs, charged couple devices, in them which break down into pixels. For AQA students, if you're doing the astrophysics option module, you'll want to look at how CCDs work and how their quantum efficiency compares to photographic and naked eye observations. For this video though, a longer exposure time means more photons hitting each pixel on the CCD. This then allows for a greater charge to build up and gives a brighter overall image. But this is not just something that's reserved for specialised equipment. Any camera on a phone from the last 15 years plus will have different settings which will allow you to adjust the exposure time. Night mode will give you a longer exposure to let more light in, and sports mode will give you shorter exposure which lets less light in for a sharper image. But also, if you're taking a general photo, depending on what part of the frame you focus on, it can adjust the exposure time. Take these two images here, for example, both taken on the same device, but with different parts of the image focused on before taking the photo. In the first, I clicked on the sky, as this was much brighter than the rest of the image. My phone reduced the exposure time to allow for better distinction between sky and clouds, but we lose clarity on the darker portion of the image. In the second, I clicked on the foreground, which was in shadow. My camera then adjusted for a slightly longer exposure time so that you can make out the differences between the different light levels here. Going on a bit of a tangent here, but if you're looking at getting into painting landscapes and are working from your own photographs, then it's a really good idea to take multiple photos, exposing short to pick up the differences in your highlights, and exposing slightly longer to pick up the fine details of the darker regions of your scene. From there, don't be afraid to adjust the brightness and contrast of photos on your computer. This can help to get you stronger images to actually work from when you're producing your own paintings. Photographic film is more sensitive than the human eye, meaning that it can detect objects, especially with the aid of telescopes, that we would not be able to see on our own. As astronomers, we observe at night and want to have the longest possible exposure time in order to pick up the faintest stars, galaxies, and whatever else we can find, really. You may be wondering whether modern telescopes have to use such long exposure time. The answer is no, as the CCDs, same as are in regular digital cameras, are even better at detecting light than photographic film. This is due to something called quantum efficiency, which compares the amount of photons detected by an instrument with the actual number of photons that are incident or incoming. The human eye has a quantum efficiency of 1%. That means that 99% of light that hits our eye is not detected. Photographic film, the sort that would have been used for these slides, has a quantum efficiency of up to about 4%, so a decent step up, but still not immense. That's why old film cameras will often still need a flash in low light to boost the light levels enough to function properly. CCDs have a quantum efficiency that can exceed 70%. This means that they can get the same brightness of image on a much shorter exposure time, and it can be easier to see fainter, more distant objects with a similar exposure time on digital cameras. Oh yeah, loads. What do you mean I need to explain it? Whilst a longer exposure time will make it easier to see fainter objects, if you have brighter objects in the same view, then these will hit your photographic film or CCD with an awful lot of photons during the exposure time. This can either lead to whiting out sections of the image where they receive too much light, or damaging the sensors on your CCD. This is actually something I have experienced doing, although quite a long time ago. For my AS level art exam, I was looking into the theme of time and descent and used long exposure photography for some of my developmental work. As you can see from the images, by keeping the camera fairly still and having the subject, my brother, move about in each one, it gave quite a dramatic effect. But then I tried to do an 8-second exposure time of water flowing through a local stream in broad daylight and knackered the CCD on my 16th birthday present. Sorry, Mum and Dad. As a tangent to this tangent, life lesson time. If you're doing photography at night from a motorway bridge, make sure you've got your flash off. Otherwise, the cars on the motorway might somehow think that you're a speed camera and be rather annoyed at you for some reason. Can't think why. Also, the position of stars changes with time in the sky, so unless your telescope tracks with the object it is focusing on, you're going to end up seeing a blurred trail through the sky instead of a clear image of what you're trying to focus on. Yes, GCSE astronomers, listen up, as this is a potential observational task that you can do during your course, or one that you might be asked about during the exam. So you can use long exposure photography to work out the sidereal day length, that is, the time taken for Earth to rotate 360 degrees. If you're in the northern hemisphere, center your image on Polaris, the pole star. This will stay fairly static if your camera is mounted on a tripod, with other stars nearby it in the sky, creating arcs of light around it. By measuring the angle these trails travel around Polaris and comparing that to a full 360 degrees, this will have the same ratio as the exposure time compared to one sidereal day. For this to work best, you want a clear view to the north with minimal obstacles blocking where star trails will be. To get as far north as possible, this will make Polaris higher in the sky and give you more circumpolar stars to observe. At least half an hour of exposure time to give the biggest angle possible, but if you can get longer than that, that's even better, and a really steady mount for your camera. And that wraps up our deep dive into exposure time on astronomy. If you've got anything to add to the topic, please do let us know down in those comments. Next week, we'll be looking at how we actually realised that galaxies existed and that our universe was much larger than we originally thought. Until then, feel free to like this video. If you haven't already, then please consider subscribing as well. And if that isn't enough, YouTube has decided that this video right here will entertain you for literal minutes and enrich your life for several days. Until next time, please continue to watch this space. Thank you.